Alright, so how y'all doing? Today we are going to cover the first practice exam. Um if you guys saw the announcement today, you saw that we're not doing molarity, right? So off the jump we could just cut out a good chunk of this review. So most of these questions are molarity, so if anything I'll probably do another review of the other practice exam, but off the jump, we don't have to worry about this is molarity. This is also molarity. This is also like look at mad molarity, right? Okay, let's start out with this. Uh Phosphine, an extremely poisonous and highly reactive gas, will react with oxygen to form tetraphosphorus decaoxide in water. So it's a bunch of words going on here, right? It gives us the it gives us the chemical reaction, right? So this right here is literally just overview, a summary of the chemical reaction below, and it's telling us calculate the mass of P4O10, right? Formed when 225 grams of pH3 reacts with excess oxygen, right? So first, let's go ahead and basically just balance this equation, and then let's focus on the answer. I mean, on the question after this. So let's just balance this equation, and I'm gonna write it out for you guys. Uh, Plus H2O, right? So what I like to do, I like to separate the reactants and the products and go from there, right? So I'm gonna write out all my givens. Starting with phosphorus, I got phosphorus right here. I got oxygen. I have hydrogen, oxygen, phosphorus, hydrogen, oxygen, right? And write out all my givens. I have 1 on this side, 3 on this side, 2 on this side. I have 4. I have 2, and I have 11 oxygens, right? Because I have a 10 here and I have 1 here, right? Right. So, boom. Okay, so off the jump, I have 4 phosphorus here, then I have 1 here. So knowing that, I'm going to want to start with the smaller side first, and we're focusing on phosphorus. So the 4, we're gonna put a 4 here. It's gonna distribute, and this side we're gonna bring it to 4. The hydrogen here is gonna get multiplied by 4. So 4 times 3 is 12, right? So yes, we got phosphorus equal, but at the same time we also affected the hydrogen, right? The hydrogen is 12. So let's focus on hydrogen now, right? We got phosphorus to be equal. Let's go ahead and spend some focus on hydrogen instead, right? So there's a 12 on this side, so I'm gonna ignore that. I'm gonna focus on this side. I want to get the 2 to the bigger number, which is 12. So this is what I'll do. I see a hydrogen here, so I'm just gonna multiply it by 6, right? And distribute that. That hydrogen becomes 12, right? Okay, boom. Also, do not forget though, we multiplied it by 6, right? Which is all good. But now that we multiplied it by 6, we also affected its distributing. So we affected the oxygen on this side. So we have 10 oxygens here, and 6 times 1 is 6. So now we have 6. We have 10 plus 6 oxygens. So that will be 16. We have 16 oxygens now, right? So we're almost done. All we need to do here, right, is balance out the oxygen. So you guys have we talked about the fraction. Luckily, we don't need to use the fraction here. Um, all we need to do, look at this side, look at this side. This side is a bigger number, so and this side is a smaller number. So I'm gonna focus on this side, right, to balance it. If you look at the 2 and the 16, what can be multiplied by 2 to get to 16? 2 times 8 is 16, right? So I'm going to put an 8 here. It multiplies it, and it's balanced, right? There we go. So let's write this out, right? We have, let me see if I get some space right here. I'm gonna write it right here. We have 4pH3 plus 8O2 goes to P4O10 plus 6H2O, right? So that's our final, that's what we end up getting, right? When we balance the equation. So this is what we're going to be left with. And now we can go ahead and look at what they're asking us to find, right? So let's go ahead and look at this right here, right? So the way I would go about this, I would read it and look for, there's always going to be one number that they give you, right? For stoichiometry, these kind of problems. Look, so calculate the mass of P4 O10 formed when 225 grams of pH3 reacts with excess oxygen. So first off, this is not important. Excess oxygen means there's a surplus of it, so we shouldn't worry about it. We shouldn't worry about it being limited. So just ignore this, right? Just ignore this and focus on this. Calculate the mass of P4O10 when you have 25 grams of pH3. So what we're starting out, what our given is 225 grams of this, and what they're asking us to find is mass of this, right? And mass is always going to be in grams, correct? So this is stoichiometry, right? And I'm gonna show you how we go about this. So we start with 225 grams pH3, but whenever we do stoichiometry equations, we want to turn it into moles. So we can't work with grams. Remember, we want to turn this into this. And to do that, we have to work with moles, right? So let's go ahead and look at the molar mass of phosphorus and hydrogen, right? So, let's look here. Phosphorus is 30 point, and just for the sake of this review, I'm going to be specific and not round. I'm going to round towards the end just to be concise with you guys. So we have our compound is pH3. So we have this plus 1.0078 times 3, right? Or you just do this, right? So, let me go ahead and plug it into the calculator. Give me 1 second. But yeah, wait, let me double check something. Give me 1 second. Okay, and the answer to that would be 33.9974. Now, probably just to make sure that you guys know what I'm doing, I'm trying to convert grams to moles. So I need the molar mass to convert grams to moles. So I basically was looking for the molar mass of pH3, right? And the molar mass is right here of phosphorus, and we got the molar mass of hydrogen right here, right? And I put 7.8, 7.9, but it's not much of a difference, right? So we need the molar mass to turn grams to moles, right? So here's what I'm gonna do. I'm gonna put what I want, or I'm gonna put what I already have on the bottom. So I already have grams, and I know that the molar mass of pH3 is 33.9974, right? And I also know that there's 1 mole for that I'm trying to get to moles, so I'm gonna put 1 mole, right? Cross this out, and I end up dividing. So let's go ahead and divide this, right? Okay, so 225 divided by 339974. That's 6.61. I'm gonna put 6.62. So we have 6.62 moles of pH3, right? Remember, we're trying to get from pH3 to P4O10. So we found the moles of pH3, and now we want to convert the moles of pH3 to the moles of P4O10, right? So how are we gonna do this? We basically set up a mole ratio, right? Mole ratio. So we're setting up, right? That mole ratio is gonna turn one different compound to another, right? And we need that. It's important. So this is how I'm gonna set it up. What I already have, I'm gonna put on the bottom. So I have pH3. If we look here, we're looking at the coefficients to find the mole ratio, right? I have 4 pH3. I have 4 moles of pH3, right? So I'm gonna put 4 moles of pH3 in the bottom, and then I'm going to put what I'm looking for, right? So I put what I already have on the bottom, and I put what I want to find on the top. So I have 1 mole. This is 1. If there's no coefficient behind it, it's 1, right? 1 mole of P4O10, right? And if you look here, this crosses out, and all we gotta do is just do the math for this, right? So 6.62 divided by 4, and it's 1.655. I'm gonna put 1.66. I'm just rounding it. You don't have to do this. I like to round it. And I end up getting moles of P4O10. Are we done? Unfortunately, no, right? We found the moles of P4O10, but if you look at the question, it's asking us the mass, right? Mass equals grams. We're looking for the grams of P4O10. So we just have one more step. We're just converting the moles of P4O10 to grams. And to do that, we're doing the reverse of the step we did here, right? So let me just show you. So 1.66 moles. And we're just going to set up a unit conversion, right? So I want to put moles on the bottom so I could cross it out. And on top, I'm going to put grams, right? And the grams is going to be the molar mass of P4O10. So let's go ahead and find the molar mass, right? We know that phosphorus is this number right here. Multiply phosphorus by 4 because we're looking for, let's write it down, P4O10. So I know phosphorus is this right here. I'm going to multiply by 4, and I'm also going to multiply the molar mass of oxygen, right? I'm just going to round this to 16. I know I said I wasn't going to round, but we'll just do it for this. We have 16, and we're going to multiply that by 10 because we have 10 16s and we have 4 phosphorus, right? So let's go ahead and do that. I'm just going to do it on my calculator. Give me 1 second. And we should get 283.896, right? So the molar mass should be 283.896. That is what we should have, right? Now, we're just multiplying the straight across, right? So whenever we're trying to turn moles to grams, we multiply. Whenever we're trying to turn grams to moles, we divide by molar mass, right? And our answer is 471, right? Grams of P4O10. So you should normally do sig figs for this. But also it really just depends on the multiple choice response. If you look here, what's the closest thing to 471, right? It would be this, right? It would be C. So our answer for this is C. That's how we're doing that. And I'm just gonna erase this because I want space for the next question, right? You guys can always go back to it. Let's see. Balance the following equation. So I'm just gonna write it out. Technically, it's more work, but technically you guys could just assess all of these and see if they're balanced. But I feel like it's easier to just do the balancing yourself, right? It's not too hard. We'll walk through it. Okay, so we have reactants and we have products. Let's write out all our givens. We have B, we have F, we have H, and we have O. B, F, H, O, right? So I have 2B right here. I have 1F, I have 1H, and I have 3 oxygens, right? On the reactant side. Let's look at the product side. I have 1B, I have 3 Fs, I have 2 H's, and I have 1 oxygen, right? This is a lot of elements in this problem, right? That's okay. So off the jump, let's focus on the top one, which is right here. B is 2 right here. We got a 1 over here. So I'm just going to multiply the 1 by 2 so I could get it to be, the same. I want it to be equal, right? So I see the B. I'm just going to multiply it by 2. It's going to distribute, of course. I'm just going to use, matter of fact, I'm going to use a different color so you guys can see it. So this B becomes 2 now, but it also affects the fluorine, the F. So the F becomes 6 because 2 times 3 is 6, right? So now let's focus on this right here. We just balanced out B, so let's just check it off. We just balanced it. Now let's focus on F. Like I said before, I like to look at the smaller side and get it to the bigger side. So we have 6 on one side and we have 1 on the other. So we're trying to get 1 to 6, so we're just going to multiply 1 times 6. And fluorine is right here, so we're just going to multiply it by 6. And that turns fluorine into 6. Now, that turns fluorine into 6, which is checked off. But don't forget it also affects the hydrogen here, right? So the hydrogen also gets multiplied by 6. And now we have 6 hydrogens on this side. And we're trying to, remember, now let's focus on hydrogen. So now we have 6 hydrogens. And we have 2 on the other side. And I want to get this 2 to equal 6, right? So it's equal to the other hydrogen. So what can I do? I can multiply the 2 by 3 to get it to 6. So I'm going to multiply this by 3, right? And it turns into 6. But it also affects the oxygen here, right? So the oxygen now becomes 3 because 3 times 1 is 3. Thankfully, though, it unintentionally balances everything out for us. So we didn't even need to worry about oxygen because while we were balancing hydrogen, we ended up unknowingly balancing oxygen, right? So if you look here, it's all balanced. All of the numbers are equal to each other. So let's look to see where our answer would be. It wouldn't be here. This is literally because you guys, just so you know, you can't add numbers to the bottom here. You can only add coefficients, right? So we know this is not it. This doesn't even match what we got. No, wait, I lied. This does match what we got. This is literally our answer, right? All right, so let's go ahead and answer number 6, right? So off the top, like reading it off the jump, I could tell it's asking for an empirical formula, right? Because it literally says what is its empirical formula, and let's just read it. Hydro. Never mind. This big word right here is a powerful reducing agent which is used as a. Okay, so this is all. This is good to know, but we really don't. This is not important to us, right? What's really important to us is this question. This is the important part. It contains 5.80 mass of percentage of hydrogen, 20.16 mass percentage nitrogen, 23.02 mass percentage of oxygen, and 50. Okay, so it gives us the mass of this big compound, right? So we know, first of all, if you were to add all of these up, all of the masses up, right, it would add up to 100, right? So it's giving us the mass percentage out of 100. All we need to do is take the mass percentage and translate it to. We take the mass percentage and we translate it to mass, right? It's literally just the mass percentage of 5.80. Its mass percentage is basically just 5.80 grams of hydrogen, right? So now I showed you guys that we basically we have the grams. This tells us the grams of everything in the compound. All we have to do is turn the grams into moles, because whenever we're doing empirical formula, we can only work with moles, right? So let's write down all of our givens. We have 580 grams of hydrogen. We have 20. Well, hold on. We have nitrogen, which is 23. No, sorry. Yeah, no, I was right. Well, no, it's 20. Nitrogen is 2016, right? Grams. And oxygen is 2302 grams. And then Cl is 51.02 grams, right? So, first of all, we have to convert all of this to moles, right? Yeah, we have to do all of that. So, let's go ahead and get some space for this. Matter of fact, I'm just gonna have to go like this, right? I'm gonna have to use up some space. So give me 1 second. Let's get hydrogen. Let's turn hydrogen into hydrogen moles. We have the grams. Let's turn it into moles, right? So we have 5.80 grams of hydrogen. We're gonna set up a unit conversion, right? Because I want to turn grams to moles, and to do that, I have to divide by the molar mass, right? So on the bottom, I'm gonna put the molar mass. On the top, I'm gonna put what I want, which is moles. This will cross out, right? So what's the molar mass of hydrogen? It would be 1.0078, right? And if you do the math here, 5.80 divided by 1.0078 equals 5.75, right? Roughly moles of hydrogen. So we got our moles of hydrogen. Let's do nitrogen now. We have 26.16 grams of nitrogen. If you look at your periodic table, the molar mass of hydrogen, or nitrogen rather, sorry, is 14.0007, I believe. So I'm just gonna round it to 14, right? That's the molar mass. So what I'll do is put molar mass on the bottom and what I want on the top. Cancels out. 20.16 divided by 14 is 1.44 moles of nitrogen, right? Now let's go ahead and focus on oxygen now. I have, let's just go like this. I have 23.02 grams of oxygen. I'm sure all of you already know the molar mass by now of oxygen. Oxygen, its molar mass is 16, right? So molar mass of oxygen is 16 grams. So I put my molar mass on the bottom and I put what I want on the top, right? So it cancels out. And 23.02 divided by 16 is 1.43, right? Is 1.43 moles of oxygen. Okay. And we got one more, which is Cl, right? Cl is 51.02, right? We're gonna do the same thing once again. I know that the molar mass of Cl is 35.45, right? So I'm gonna put the molar mass on the bottom, and on the top I'm gonna put what I want to get to, which is moles. Cross it out, and 51.02 divided by 35.45 equals 1.43 as well, right? So when we do empirical formula, we take our smallest number and we divide it by everything. So if you look closely here, the smallest number would be oxygen and Cl. They're both the same. So what I'll do right here is divide everything by 143. That's the smallest number out of everything here, right? Divide everything by 143. And basically just find what that would equal for everything, right? So I'm going to put some space over here, right? And write out everything that I got. So this right here is hydrogen. So hydrogen, we're going to write out what it gives us when we plug it in. So 5.75 divided by 1.43 is 4.02. Right? Let's look at nitrogen next. 1.44 divided by 1.43. I think that one is pretty obvious. It's gonna be 1, right? Or it's gonna be roughly 1. So let's just go ahead and show you. It'll be 1 point. It's roughly 1. It's 1.006. So I'm just gonna put 1 down for that, right? Unless it was like 1.5 or 1.4, then you know that's not. It's not technically 1, but it's 1.006. So I'm just gonna write it down as 1, right? And these two are being divided by each other. So when you divide something by each other, it's gonna equal to 1, right? So 1.43 divided by 1.43 is 1. So oxygen is 1, and chlorine is also 1. So everything except hydrogen is higher than 1, right? And if we put this together, right? Let's put this together. Hydrogen would be 4. Nitrogen would be 1. Oxygen would be 1. Chlorine would be 1. So let's find the best answer according to what we just got, right? Well, first off, this is not 4. This one's not 4 as well. This one is 4, but we know that chlorine is not 2, right? This one is not 4, and chlorine is 9, which is not it. So our best choice would be this right here, right? It matches what we got to the T. We got H4, N, which is 1, O, oxygen, which is 1, chlorine, which is 1. So boom, that's our answer. Okay, let's go to 7. Balance the following equation for the combustion of benzene, right? So this is a balancing equation problem, so let's go ahead and write it out, right? Let me get a little bit closer. C6H6 plus O2. Hold on. I'm gonna leave some space. Plus CO2, right? So let's go ahead and write all of our givens. We have carbon, hydrogen, oxygen. It's a combustion reaction, by the way. So we know we're dealing with like a lone oxygen. Let's just write how much of everything that we have, right? Right. Currently, we have 6 on the reactant side, 6 carbon, 6 hydrogen, and 2 oxygens. Over here, we have 1 carbon, 2 hydrogens, and 3 because there's 1 here and there's 2 here. So there's 3 oxygens right now on the product side, right? So let's get the bigger number. Let's get the smaller number. So right now we're focusing on carbon, right? I want to get the smaller number to the bigger number, so I'm going to multiply 6 times 1 so I can get it equal, right? So 6 times 1 is 6. And when I do that, this carbon becomes 6, right? So we just got this done. But remember, this distributes. So now I have 6 times 2 is 12 oxygens and 1 oxygen. 1 plus 12 is 13. So I have 13 oxygens on the product side, right? Give me 1 second. I have 13 oxygens on the product side. So let's go down to hydrogen, right? I see a 6 and I see a 2. Off the jump, I want to bring 2 to 6 because 2 is a smaller number and I can multiply 2 by 3, 2 times 3 to get it to 6, right? So let's look at the product side. I see the H2, I'm going to multiply it by 3, right? This way the hydrogen becomes 6, but it also affects the oxygen, right? So the oxygen is going to become 3 because 3 times 1 is 3, and this one is 12, right? So 12 plus 3 is 15. So off the jump, I'm looking at this and I'm seeing that I have 2 oxygens on the reactant side and 15 oxygens on the product side. It's something I can't multiply them to. Like, yes, I can mess with these, but in order to get this proper, I would have to mess with everything else, and that's a lot of work. So I'm going to use a little trick, right? I'm going to make a fraction out of these oxygens. So my fraction is going to be 15 over 2. So think about it as what I want to get to, I'm going to put on top. What I already have, I'm going to put on the bottom, right? So I have 2. Put on the bottom, I wanted the 2 to get to 15, so I'm going to put the 15 on the top, right? This fraction is going to go right here, right? It's going to go right there. Let's write that in a way that you can see it, right? So give me 1 second. It's going to be 15 over 2. That is going to affect the lone oxygen on the reactant side, right? And then I'm going to multiply this whole reaction by 2. And it distributes, right? But this 2 is going to cross out here. So the multiplying thing, it doesn't affect this oxygen here. But it will affect every other compound on the reactant side, right? So basically, I keep the 15. Like, I take out the 2 here, I keep the 15, so the lone oxygen becomes 15. And I multiply everything by 2, right? So let's go ahead and rewrite this. So I'm just rewriting it, multiplying everything by 2 except the lone oxygen. And this is what I get. This is what it turns into when I multiply everything by 2 and I keep the lone oxygen as 15, right? And let's just check to see if any of the answers match this up, right? So off the jump, we know this one's wrong because there's supposed to be a 2 in front of that. This one's supposed to have a 2 in front. This is wrong. This one has a 2 in front. It has 15, which we also got. It has 6, which we also got, and it has 12. So we know this is the our answer that we're looking for, right? We know that's our answer. Now let's go to 8. Aluminum will react with bromine to form aluminum bromine, right? So it's basically giving a summary of the chemical reaction we're looking at. It's explaining what it is, right? So this is our chemical reaction, and we have to balance it. So let's go ahead and balance it first. This is giving a summary of what it is, and this is exactly what it is. So we're gonna balance out this chemical reaction. So I'm gonna use the space here to do that. I'm gonna just do this over here, right, guys? So aluminum plus bromine goes to, okay, so let's go ahead and do this. Let's write out all our givens. I have aluminum on this side. I have bromine on this side. I have aluminum, bromine. I'm gonna write out how much I got. I got 1 over here. I got 2 over here. I got 2 aluminums. I got 6 bromines, right? So off the jump, I'm seeing that the aluminum is not equal, right? The bigger side, the product side has 2. Reactant side has 1. I want to multiply the 2. I want to multiply the 1 times by 2 to get it to 2. So I'm going to put a 2 in front of here, right? So it just becomes, oh. It just becomes 2, right? And then, so now these 2 are checked off. It's equal, right? So all I gotta do is worry about bromine. Bromine, there's a 6 and there's a 2. There's a 6 on the product side and 2 on the reactant side. So I want to get 2 to 6, right? Because 2 is a smaller number, and I can get it to 6. I can multiply 3 times 2 to get it to 6, right? So I'm going to multiply the reactant side of bromine by 3. And then this way, the bromine over here would become 6, right? And it's balanced. That's our balanced equation. Let's go ahead and write it here. 2 aluminum, 2 aluminum plus 3 bromine turns into aluminum bromine, right? It's balanced out. That's our balanced equation. And let's go ahead and read what it's asking us for. How many moles of aluminum are needed to form 2.43 moles of aluminum bromine, right? So it's giving us 2.43 moles of aluminum bromine, right? And it's asking us to find the moles of aluminum that we need. All right? So let's write down our given. We're given 2.43 moles aluminum bromine. And with this, we're asked to find aluminum, right? So luckily, it already gave us moles, right? So remember how I said whenever we're doing stoichiometry or equations in a chemical reaction, which would be right here, we have to convert it to moles. We can only work with moles. So off the jump, I can make a mole ratio, right? To turn aluminum bromine into aluminum, right? So I'm going to make a mole ratio. And remember how I did the mole ratio. What I already have, I put on the bottom. So if you can, as you can see here, there is no coefficient right there. So I'm going to go ahead and put this is one coefficient there. It's imaginary 1. So we got 1 on the bottom. We already have aluminum bromine. and we're trying to get to aluminum. And if you look here, there is a 2, right? So I put 2 right here, 2 moles of aluminum. I cancel this out and just multiply it straight through, right? So let's go ahead and do that. 2.43 times 2. We got 4.86 moles of aluminum, right? And if we look here, what matches our answer? What matches our, this right here matches our answer, right? B is 4.86. That's exactly what we got, right? So it isn't too bad at all. It's doable. That's what we get there. Now let's move on to 9. According to the following reaction, how many moles of iron hydroxide can form? Okay, this is a molarity problem, so we're going to go ahead and not do this, since that's not going to be on the test. Let's look at this. Oh, this is perfect. This is, let's read it. Aluminum oxide used as an absorbent, or we don't need to know this, so I'm not even going to read it. It's just basically this basically summarizes the chemical reaction. It's a summary of the chemical reaction. I would skip reading it if I were you and just focus on this right here, right? So a mixture of 82.49 grams of aluminum, 117.65 grams of oxygen is allowed to react. What mass of aluminum oxide can be formed? Okay, so this is a limiting reactant problem, right? So we just learned that today, limiting reactants, and it might seem a little intimidating, but all you need to know is we're trying to find the smaller of the two reactants, right? So this is the reactant side, this is the product side. Let's write it out. We have 4Al plus 3O2 goes to 2Al, right? 2 aluminum oxide, right? This is the reactant side, this is the product side. So a good way to know if you got a limiting reactant problem is if they give you the mass of both reactants, right? So they give us the grams of this reactant and the grams of this reactant. So we have two things that we know. We know the mass of aluminum and we know the mass of oxygen. So we have to find out which one is the limiting reactant. And limiting reactant just means smaller of the two reactants. So let's just go ahead and do the work real quick. I'm gonna start with aluminum, right? And then go to oxygen. So aluminum is, they say it's 82.49 grams. That's how much aluminum we have. And we're basically going to turn to find out which limiting reactant is smaller. All we have to do is basically just turn it into this right here. We have to turn both of these reactants into this. And whatever gives a smaller answer is our limiting reactant, right? So let's go ahead and do that. Let's go ahead and turn aluminum into aluminum oxide, right? Give me 1 second. Alright, right? So first thing we're gonna do, every time we do a stoichiometry or limiting reactant problem, we're only working with moles, right? So we want to turn the grams into moles. So we have aluminum, and luckily it gives us the molar mass of all of the elements we're working with, right? So we're turning grams to moles. To turn grams to moles, we divide grams by molar mass to turn it into moles, right? So let's put what we want on top and put what we already have on the bottom. And we know that the molar mass is 26.98, right? And we're just gonna divide that. 82.49. Just double check that's what it is. Divided by 26.98, right? And we get 3.05, right? we get 3.05 moles of aluminum, right? Um, Now let's find. So we found aluminum. We found the moles of it in the. Now let's find the moles of oxygen, right? This is what we do. So we know that we have grams of oxygen given right here. We have 117.65 grams of oxygen, and it gives us the molar mass. So we're gonna set this up to get moles. We put moles on the top, grams on the bottom of the molar mass. Cancel it out and divide it, right? So 117.65 divided by 32. That equals 33.67. Yeah, moles of O2. So the limiting reactant is whichever is smaller between the two, right? And in this case, the aluminum is smaller, so it's the limiting reactant. But are we done? We found the limiting reactant, right? But as you can see, it's not asking us for the limiting reactant. Like, this is only one step of the problem. It's asking us what mass of aluminum oxide can be formed with our limiting reactant. So when it's asking us to find the mass of something, and it's also a limiting reactant problem, we're gonna take the limiting reactant and we're gonna use it to find aluminum oxide, right? So we're gonna take it to find aluminum oxide. So if you see here, we already have moles of aluminum, right? We don't have grams, we have moles of aluminum. All we need to do to find or to turn the moles of aluminum to moles of aluminum oxide, all we need to do is use the mole ratio, right? Right? So let's set up a mole ratio. Okay. On the bottom, remember the mole ratio. It's what we're gonna put on the bottom is what we already have. What we're gonna put on the top is what we want to get to, right? So if you look here at this balanced equation, we know that aluminum is 4, and we already have aluminum. So we're gonna put what we already have on the bottom, 4 moles of aluminum, and we're gonna put what we want to get to on the top, 2 moles of aluminum oxide. Right? Cross it out and put the moles through the ratio, right? So 3.05. Let's look at the ratio. It's 2 divided by 4 times 2 divided by 4, and we get 1.5, right? Or 1.52 rather. 1.52 moles of A2O3. Are we done though, right? Because let's look at what it's asking us for. What mass of aluminum oxide can be formed? So we found the moles of aluminum oxide, but now we need to find the mass of it, right? So this is what we're gonna do. All we're gonna do is convert moles to grams, right? And if you remember correctly, you multiply by the molar mass to turn moles to grams. So we have moles of aluminum oxide, and all we're gonna do is set up a unit conversion. We're gonna put what we already have on the bottom, and then we're gonna put what we want on the top. And luckily, it gives us the molar mass of aluminum oxide. It's 101.96, right? That's what it is, right? So I'm just gonna multiply this. 1.52 times 100 and 1. So 101.96, I believe. And our answer is 1.54, 154.9, right? So our answer is 154.9. Sorry. And that's grams of aluminum oxide, right? So if we look at the best choice, right? Our best answer that's closest to this is this right here, right? So that's gonna be A, right? So we found 10. And now let's look at 11. Um, like I said here, this little thing is a summary of the chemical equation. Um, let's read the question, right? A mixture of 41 grams of magnesium and 175 grams of iron chloride is allowed to react. Identify the limiting reactant and determine the mass of the excess reactant present in the vessel wow, so this is a lot of words, right? So how would we go about this, right? So all we need to do here is basically we have to find the moles of, and it says, so we have to do two things. We have to find the limiting reactant, and what we also do is have to find the grams of we have to find the grams of whatever is not the limiting reactant. We have to find what's left of that, right? When we do this problem. So I'm gonna pick the easier one. So to find the limiting reactant, right? It gives us the mass of this one, of these two reactants, and it's telling us to find which one is limiting, right? So I'm just gonna put it through there. I'm gonna turn both reactants to iron and see which one is smaller, right? So let's go ahead and do this. So we're gonna start with magnesium, one of the reactants, and we know we got 41 grams of magnesium, right? And remember, when we do stoichiometry, we don't want to work with grams. We can only work with moles, right? Remember that. So this is what I'm gonna do. I'm gonna turn the grams into moles, right? Set up a unit conversion. And luckily it tells us the molar mass, right? So I put what I already have on the bottom, and I put what I want to get to on top. And also just read the question, right? It gives us two values, and we know that these are both iron chloride and magnesium are both the reactants. When you're given two numbers, we know that it's the limiting reactant problem. And it literally says identify the limiting reactant. So it's pretty straightforward. We put moles on top, and we put the molar mass on the bottom, right? Cancel it out, and just divide. So 41 divided by 40, 24. 24 point what? 31? That equals 1.68, right? 1.68 moles of magnesium. Now let's find the limiting reactant of iron chloride, right? So we're told that we have 175 grams of iron chloride, right? Fe2Cl. Alright? So, or rather, sorry, FeCl3. And remember, when we do stoichiometry and limiting reactant, we can only work with moles. So we're going to set up a unit conversion, and we're going to put what we want on the top, what we already have on the bottom, which is the molar mass, and it's given to us, right? It's 162.2, right? Cross this out and divide. So 175 divided by 162.2. And that is 1.07, right? So 1.07 moles of iron chloride. So off the jump, we could eliminate a couple of problems here. So we already know the limiting reactant is iron chloride, right? Because this is bigger. Limiting reactant is the smaller of the two. It's the smaller number, right? So let's go ahead and look at um, what's bigger, right? Or what's the limiting reactant? What's smaller? So we know magnesium is not the limiting reactant. So anything that says magnesium is incorrect. And we're narrowing it down to two choices. Um how many so we're figuring out, right? We have all these choices knocked out, and we're trying to figure out how do we find the excess, right? Of whatever is not the limiting reactant. So remember, whatever is smaller of the reactant is the limiting reactant. So whatever is smaller of the two is the limiting reactant. We found out that iron chloride is the limiting reactant. So what we do here basically is we convert, or we have these two react together, right? So to find the excess, or to complete the reaction, we have to basically um, kind of do stoichiometry between the two reactants, right? So it's basically what we've done before. So let's just go ahead and walk through it, right? So we have 1.68 moles of Mg, right? And what we're gonna do, we're just gonna go ahead and well, rather, we're just gonna go ahead. Sorry about that. We're gonna turn this to Mg, right? So it's basically just to find the excess of, or to try and find the true excess of it. We're just going to take the limiting reactant, turn it into Mg, the excess reactant, and then from there move forward, right? So let's just go ahead and walk through it. So what we'll do here is use the unit conversion, or a mole ratio rather. So we already have moles, right? We already given moles. And to do stoichiometry is basically just to use moles in the mole ratio to turn one compound to a whole different compound, right? So we'll go ahead and do the mole ratio. What do we have? We know that we have 2 moles. So what we have is FeCl3, and that is 2, right? And what we're looking for is magnesium, which is 3. So we put 3 up top, right? And cross this out, and it's basically plug that in, right? So 1 point, let's just see what we're looking at. 1.07 times 3 divided by 2 equals 1.605, right? So we know that when turning the limiting reactant, or fusing, or going through with the reactant between, or going through with the reaction between both reactants, to find the excess, we know that it would equal to 1.605, right? So let's just get some space here. So it would equal to 1.605 moles of magnesium, right? So we found, right, how much would remain if we were to if we were to take the limiting reactant and have a reaction with the excess reactant, right? So we found it, and basically what we're going to do, and I want to be very precise with my wording when I say this, because technically you guys haven't really seen this during the professor hasn't really gone over it. So basically what we do is we look at how much magnesium was used. So we were trying to find the limiting reactant, and we saw that we got this answer. Aside from this, let's ignore this right here, because we don't need this anymore. We already used it. We found this is the limiting reactant, and we also found this is what's left, or this is what was consumed, and we're trying to find out what is left, and this is what was left, right? So in order to find out what remains, because we found what how much we used for how much magnesium we used for this reaction, and now we have to find out, and then we found out what's left of the reactant, right? Um, when the two reactants, go through the reaction. So to really find out this, we have to subtract 1.605 moles of Mg with 1.68 moles of Mg, right? So let's go ahead and do that. Right? And just make sure it's right. And let's see what we get. We get 0.075. We get 0.075 moles of Mg, right? Now, are we done? It's asking, well, first, it's asking for the mass. Determine the mass, right? So all of these answers are in mass. They're in grams. So all you gotta do is turn this into grams, right? So I'm gonna multiply it by the molar mass to get it in grams. And I know that the molar mass of Mg is 24.31, right? As said here. So I'm gonna put what I already have on the bottom and put what I want on top. 24.31, right? And if we multiply this, right? We get 1.8, right? You get 1.8 grams of Mg. And now let's look at our best, what matches this to the fullest, right? It says 87 grams of magnesium remain. That's way far off what we got, right? But what does match is 2. We could round this 1.8 to 2. So E would be our closest answer, right? We know the limiting reactant is iron chloride. And we also know that what remains would be 2, right? So let's go to 12. Just gonna erase all this. Oh, yeah, 12. A salt water is A, a mixture, B, a molecule, C, only one compound, D, an atom, and E, an element. So this is what the professor talked about. This was talked about a very long time ago. This was probably your guys' first, one of your first topics when we were talking about, remember, mixtures. So it says mixture, molecule, only one compound, an element, an atom. So I want you guys to think about an example. Let's think about examples of things, right? So we think of an example of an element. We think something like oxygen, right? It's an element, right? Let's think about an atom. An atom is basically, I would think about, when I think about an atom, I would think about, for example, let's look at sodium chloride, right? And it asks for an atom of sodium chloride. There's one chlorine, so I'd put one atom of chlorine, right? That's one thing I would think about. Only one compound. An example of that would literally just be a compound. In a molecule, so we're just thinking of examples of all of this, but I think the best way to do this is think about, what did we compare salt water to when we first started? So we were talking about a specific thing in the beginning of, we were talking about topics, and one of them, the topics we were talking about were pure substances. And if you remember, one of the pure substances was mixtures, right? And mixtures we know are different from elements, right? Or compounds for that matter as well. So a mixture is something that can be physically removed. It can be, I guess, pulled apart from each other. Like salt and water, salt can be removed from the water, scientifically. Like an element, or an element cannot be removed, right? It cannot be changed, right? Salt water could be messed with, right? So mixture, there's two types of mixtures. There's homogeneous and there was heterogeneous, right? And an example of there was an example given of a homogeneous and a heterogeneous, and homogeneous mixture is uniform throughout. It's the same. And an example of homogeneous mixture would be salt water. That's something that, if you guys remember correctly, that was one example given. So it's basically just using what you like remembered about mixtures and pure substances. And when you think salt water, you should think of mixture, right? So let's go to 13. So off the jump, I know this is a temperature problem. Convert 82 Fahrenheit to the Kelvin scale. So I have 82 Fahrenheit. And I'm going to give, so basically, when you guys look at your reference table, the temperature is given, right? So I'm going to try my best to follow the conversions that are given to you. So if I'm just going to pull it up, and so I could write it down, right? But it's also a little bit of knowledge of how exactly to target or how exactly to go about the problem. So if we look here, we have Fahrenheit. And if you look at your conversions, you know that you can't convert Fahrenheit directly to Kelvin. You can't do that. But what you could do is convert Fahrenheit to Celsius and then Celsius to Kelvin. So that's the route we're going to take, right? So let's write down, and this is going to be on your reference table. I know that if I wanted to find Kelvin, and I was given, if I wanted to find Celsius and I was given Fahrenheit, I can use this equation, right? I can use this equation right here. So I'm trying to turn Fahrenheit to Celsius and then Celsius to Kelvin, right? So I just plug this in straight through, right? So let's go ahead and, first of all, let's just write it out, right? This is all that this is, right? So I'm going to do it like this. That equals 27.7, right? I'm just going to round that. And we turned it into Celsius. We just turned Fahrenheit into Celsius, right? That's what we did right there. Now we gotta turn Celsius into Kelvin, right? And I don't think this is on your, well, it is on your, so you have a conversion right here, like this. 1 Celsius basically equals 273.15 Kelvin. And I could manipulate, algebraically, I could manipulate this equation, and I could basically turn it into this, right? I could turn it into Kelvin equals Celsius plus 200, right? So this is what I'm gonna do, right? If I have 27.7 Celsius, I can basically plug it into here. I could plug it into here and find my answer from there. So basically, I'm gonna take 27.7 plus 273.15, and I end up getting 300, right? I end up getting 300, and let's see what matches that, right? Let's see what matches. What exactly is it? It's 300.85 Kelvin. Well, let me write that a little better. That's our answer, right? If we look here, what matches the answer? This doesn't, but this is the closest, right? So that's our answer. Now, let's go. down to 14. An extensive property. So we got extensives and intensive properties, right? If you guys remember about this, so intensive and extensive properties, it basically refers to what is dependent on the matter of the object and what is not dependent on the, like, what physical characteristics is dependent on the matter of the object and what isn't, right? So if you guys remember correctly, intensive properties, they don't depend on matter of object, don't depend on matter. And at the same time, extensive properties depend on matter, right? Present. So it's asking us, an extensive property is always strongly dependent on external conditions. So that was not, so when we think about extensive, we think about depending on matter, right? So external conditions don't depend on like in the external conditions like rain or whatever, it doesn't affect the matter of the object, right? So we know this is wrong. Independent of the quantity of matter observed, that is not true, right? Extensive property, an extensive property depends on matter, right? It's dependent. It's not independent of quantity. It's dependent on the quantity of matter observed. So we know this is wrong. Is a unique value regardless of the measurement conditions. So, this is an interesting question or answer, and I mean a unique value. I don't think it would be considered a unique value regardless of the measurement conditions. Like it's still it's dependent on measurement conditions. It's not unique to that. So I wouldn't mark this. Even if you didn't mark this, you could choose the best answer, right? So let's look at, even if we weren't to mark this, let's look at the other answers there, right? Difficult to measure. Matter of an object is not difficult to measure, right? We found many ways to measure it. There's many ways to measure the matter of an object. Dependent on the quantity of matter observed. So this is the best answer, right? Because it literally gives the definition of an extensive property. Extensive property depends on matter of object. Dependent on the quantity of matter. It's dependent on matter. So that's the best option there. Let's go to 15. The following measurements were made by a group of students using the same balance and a 25-gram weights, right? And so they're trying to, so the weight is 25, and as you can see here, everyone here were not, like, they didn't get too close to 25, right? So this is all 23, 24, 23, but it's not 25, right? So the data would be considered. Okay. If you guys remember correctly, accuracy refers to how accurate what you got is close to the actual answer, right? So if we're talking about, let's say, a circle and you're throwing darts, let's say you have two circles, you're trying to throw darts in a smaller circle. If all three darts hit the small circle, or if let's say one dart hits a small circle, you're accurate, right? You're accurate to what you need to get to, right? Let's say three darts hit that small circle. You're precise and accurate because you got you found your target, you had your target, and you hit that target 3 times. You were accurate in getting the target, and you're also precise because you got it 3 times in a row, right? So accurate would be hitting target, and then precise would just mean hitting same spot multiple times. Right? Okay, so, and that being said, we know that the target is 25, right? 25 grams. And um we're trying to see if the students are precise, accurate, or precise and accurate, right? So let's look at the options. The data would be considered accurate and precise, precise but not accurate, neither precise nor accurate, systemic error. So we got A, accurate and precise. Let's see. So none of these people hit 25 whatsoever. So in the goal, the target is 25. So therefore, it doesn't seem like they're accurate. So off the jump, we know A wouldn't be the answer, right? It doesn't seem like they're accurate. None of them hit 25. Let's look at B. So it's 2 and 4, right? Or yeah, 2 and 4, or 2 and 5. It's 2 and 6 rather. Sorry. Accurate but not precise, and evidence of large random errors. So there's nothing seems to be random about these results, right? Because they're all close within each other, right? It's not like you got 23 and then you got some like a far number like 20, right? It all seems to be pretty close, right? So there's definitely no evidence of large random errors. There's no large difference in the numbers they all got. And it says accurate but not precise. We established that they're not accurate, right? None of them hit 25, right? So B is definitely not the answer. Look at C. Evidence of a systemic error. And then we have precise but not accurate. So, boom, we know that they're precise, right? Because look, look how close they are to each other. 23.97, 23.98, 23.96, and then you got this right here. They're all very close to, extremely close to each other. They're only like 0.004 off, right? They're extremely close to each other. So they're very precise with each other, right? So we know that, yes, this is correct, right? It's 3, but also it's asking evidence of a systemic error. So that's actually a plausible cause, right? Because if all four trials, if all 4 trials are not hitting the target, there could be a chance of a systemic error. That means that an error that affects everyone, that affects all trials. It could be an error that's far-reaching to everyone who's participating, right? So that could be true, right? So we're just gonna underline it C and keep going. Neither precise nor accurate. Well, we know that they are precise. We know that they aren't precise, but they aren't we know that they aren't. We know that they are precise, but they aren't accurate. So neither precise. It's not true. They are precise. Now let's look at all of this right here. Let's look at this right here. So we already established that there is no evidence of large random errors, and that's what this one is claiming to be. So we know this is not the answer. And the best answer is C, right? It makes the most sense. They're precise, and there could be a systemic error. Let's look at 16. A sprinter runs exactly 20 meters in 19.98 seconds. This one looks fun, right? What is her average speed in miles per hour? So we're given 200 meters per second, right? But it's 19.98 seconds. And it's saying what is her average speed, right? So first off, they gave us an incomplete value, right? because we have 200 meters up top and 19.98 on the bottom, right? So all we have to do is divide the two, right? So 200 divided by 19.98 is 10 meters per second, right? So reality is the sprinter is going 10 meters per second. And we're trying to go from meters per second to miles per hour. And let's look at our so I'm going to refer to your conversion chart that's going to be on your test. So I know that there are 1.61 kilometers per mile, right? Right? And let me just double check that. Just double check that. Yep, there's 1.61, right? 1.61 kilometers in a mile, right? And we already know the conversion with hours, right? So I'm gonna do what I told you guys. I'm gonna focus on the top conversion, right? Because this is a unit of measurement, and this is unit of time. They're two different measurements, right? Or they're two different units. And I'm gonna focus on one each. So I'm gonna focus on the top first. I'm gonna try to get meters to miles. So the way I can do that, I can't just go from meters to miles. But what I could do is go from meters to kilometers to miles, right? So let's set up a conversion. I know that there's 1,000 meters in 1 kilometer, so I'm gonna put what I already have on the bottom, meters, and I know there's 1,000 meters in 1 kilometer, right? And put what I want on the top. Cross it out and divide it by 1,000, right? That's 0.01, right? And we're not done, right? We still have to turn kilometers to miles, right? So I'm gonna put what I already have, km. I have kilometers up top. The bottom, and what I want up top. There's 1 mile and 1.61 kilometers, right? Cross this out, and I'm dividing it by 1.61, right? So there's 0.006 miles, right? In a second. Right? Now, let's say we finished the top, right? We got it to miles, but now we want to get the bottom. We want to get the bottom to hours, right? We got the top to what we need to get to, and now we need to get the bottom to what it needs to get to, which is hours. So luckily we know, or we should all know, our conversions of time, right? So we're trying to convert seconds to hours. We can't just jump from seconds to hours, but we could go from seconds to minutes to hours, right? So you basically set it up like this, right? You want to cross it out in a way that you want to set it up in a way that it could be crossed out, right? So essentially there's 60 seconds in 1 minute, right? And I'm setting it up so I could cross it out. And all I gotta do is go like this, right? 0.006 times 60 equals 0.36, right? 0.36 miles per minute, right? But I'm not done because I have to get minutes to hours. I'm going to put what I want up top, what I already have up top, because I want to cross it out. I know that there's 60 minutes in 1 hour, right? Cross this out and multiply it. And I get 21.6. It equals 21.6 miles per hour, right? That's what I get. Let's look at our best choice, right? Let's look at what our best choice is, right? So for 16, it's really about being the most exact Um, and this specifically is really about sig figs. So I would say that um, don't do what I did in rounding. You want to make sure you're not rounding like that. Um, I would try to keep it unrounded and follow sig figs, right? So the sig figs here is 4 sig figs. And the smallest number of sig figs, I would just follow the smallest number and also round it to my, so the smallest number was technically 2, but I would round it to the best of my ability, right? So um the best answer for us right here is D, right? 22.4. So it really just depends when you're doing problems like these multiple choice. Make sure that you aren't rounding it until the very end. I have a habit of rounding it while I'm doing it, but just to be sure, make sure you don't round it to the very end, right? Um, let's go over here. What is the answer to the correct number of sig figs of the following calculation, right? So we have multiplication and division, right? So off the jump, let's just find the smallest number of sig figs here, right? This is a pretty straightforward question. This has 1, 2, 3, 4 sig figs. 1, 2, 3, 4, 5 sig figs. And this one has 3. So considering this, we have the smallest number of sig figs is 3. So knowing that, we're just gonna divide it like, or we could just look at our best responses. You really don't even need to answer this question right here. Like, you don't even need to do the math. You kind of just look at the sig figs here, right? This has 4. This has 2. This has 5. This has like 6, I believe. Yeah, this has 6. This has 3, right? And we know we're looking for 3 sig figs, right? That's our answer right there. Another sig fig problem. Okay, so this one, you have to go about it a little bit differently, right? We have 2 rules here. We have subtraction, we have addition, and we have division. Division follows sig figs, and subtraction, addition. Well, division and multiplication follow least sig figs. And addition, subtraction follow least decimal points, least number behind decimal points. All right. So, how should we go about this? We have, well, how I would go about it is focus on the top first, right? Let's solve the top first and simplify the top according to how the rule, right? So let's look at how many decimal points are behind what's the least number of decimal points in the addition problem. And if we look here, this has 3, this has 2, this has 2, this has 2, so the least number is 2 behind decimal points. I'm gonna put it like that just to remind myself. And looking here, the least number of sig figs is 1, 2, 3, 4, 5, 6. Right? Right. So we have 6 sig figs, right? So we have a lot of sig figs. Our answer here is gonna be based on this, and then we're gonna divide it based on this, right? So we know that we're gonna have 1, 2, 3, 4, 5, 6 sig figs. So let's go ahead and plug it in, right? Okay. 41 point 0.02 0.003 plus okay, and we know right here that we're gonna change this according to the rule, right? So we're supposed to have the least of 2 numbers behind decimal point. So what I would do right now is put it like this. and simply divide it by the number you see on the bottom. So we know this is the number we had on the bottom. And by doing that, we get this long number, right? And we're gonna follow the sig fig rule. So 1, 2, 3, 4, 5, 6. We're supposed to keep 6, right? So let's write it out. 1, 2, 3, 4, 5, 6, right? And we're basically just seeing what has the best answer according to this, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. This has 5. But this is not gonna work. And if we look at this, the 9 also rounds to the 4, to the 3. So that 9 is gonna change this to a 4, right? So we know this is not gonna work. 1, 2, 3, 4, 5, 6. This is just not right, right? These two are obviously not 6, right? So this is our best answer.